In this follow along, we're going to examine PCC as an oxidizing reagent. And we've seen this in organic chemistry too, so this is another review. I've drawn the PCC reagent to the right here. It stands for pyridinium chlorochromate. And what you'll notice about PCC is that we are not going to be using this reagent under acidic aqueous conditions, as we saw in the Jones oxidation. Okay, so this is not present. It is not acidic, nor is it aqueous, and that's key. Let's take a look at oxidizing a primary alcohol. The first thing that's going to happen, and it looks very similar to the Jones, but we have a much better leaving group. We have a chlorine, and we don't have any protic systems, right? We don't have water, we don't have acid. The oxygen is going to exchange out with the chlorine. Very similar to what we saw in Jones. So I'm going to 1, 2, 3. I'm going to draw it in the opposite direction for no other reason than it'll just look very similar to our Jones oxidation we just covered. The intramolecular deprotonation is not occurring, right? This O- can't reach over across itself to the other hydrogen. So there is a proton shift, but I want to remind you that proton shifts don't always occur intramolecularly. Okay, this one would be very difficult. Understand that we have this pyridinium system here, which is effectively our shuttle. It's our proton shuttle. The O- can gain its proton from the pyridinium system, and then the resulting pyridine can take off the proton that is extra on the oxygen internally. So I want you to understand that it's the system that helps to shuttle the protons. It's, you know, and we might write it in a shorthand and say, oh yeah, there was a proton exchange, you know, but understand it's not, the O- is not reaching over and grabbing. It's provided for through the medium that we're in, right? That's what the pyridine is there for. It's a weak base, and it's our proton transfer vehicle. Ultimately, we get to the species that we need to get to. And again, we're going to undergo an E2. Our chromium is going to get reduced, and our carbon next door, the carbon that has the oxygen on it, is going to be deprotonated by the pyridine that's in solution. In an E2 fashion, forming the new pi bond, where the chromium leaves gaining the electrons. This gets us to the aldehyde, and we stop. What was it that allowed us to continue going forward to oxidize all the way to the carboxylic acid in the previous example? If you remember, it was the fact that we were doing it in acidic water, aqueous acidic medium. That's what allowed the 1,2 addition to form that hydrate intermediate to continue the oxidation process. But the aldehyde is the aldehyde. It's not an alcohol. It can't react with another chromium reagent. And we don't have any acid around. So what we do have around is the pyridinium system. The counter ion is the chlorine that got knocked off in the first step. Right? That chlorine that got knocked off, that's chlorine minus. So we form this pyridinium chloride salt, which is neutral. And the solvent we use is dichloromethane, which is non-aqueous. It's a very dry solvent. And we keep the aldehyde intact, and we stop it from over-oxidizing all the way to the carboxylic acid. So PCC is a nice way where it just does the SN2E2, and it cannot form that 1,2 addition intermediate for lack of water and acid. We keep it dry, and we keep the system neutral, right? We have a salt, and the pyridine acts as a buffer to keep that extra proton, those proton sponges, right? That's what's sopped up by the pyridine base. So we can stop at the aldehyde. The fact of the matter is, though, this PCC reaction still uses chromium, which is not great. And again, industrially, not the best way to do large batches of oxidations.